So hello and welcome to this first video lecture here in the course on molecular modeling. The first topic that we will cover is molecular mechanics. So what we aim at in molecular mechanics is to obtain a very simple description of molecules and a description based on classical mechanics. So for a moment what we do is that we completely neglect the fact that molecules in fact are built up of atoms having a nuclei and electrons, but we consider molecules as being composed of some balls which are connected by springs. Now, in order to calculate the energy for such a molecule here in a classical mechanical description, we need first to define the different kinds of motions and interactions that takes place in such a molecule here. As illustrated here for the water molecule here, we have first of all the bond stretching motion up here. We also have the bond bending motion, and for molecules which are a bit more complicated than water, we also have a torsion about a bond. In addition to these energy terms, we also have electrostatic interaction energies and we have van der Waals interaction energies. So our job here will now be to write up some simple analytical functions that can be used in order to calculate the energy due to these motions here and interactions here, and then to use this energy expression in order to calculate the energy for a molecule. And this defines what we call the force field. So the term force field is used for a molecular mechanical description of a molecule and consists of a set of simple functions that can be used to calculate the energy of the molecule. What comes out of such a calculation here is an energy, namely the force field energy, and this is now the energy of the molecule at a given conformation evaluated using the classical mechanics. So these different motions and interactions that I introduced on the slide before, we usually group them into 4 different boxes. The stretching, bending and torsion refers to the bonded energies. So these involves interactions between atoms which are directly bonded. The van der Waals and electrostatic interactions are referred to as the non-bonded energies, since these involve interactions between atoms which are not directly bonded. We also have cross terms, which is due to the fact that the stretching, bending and torsional motions in real molecule are not completely separate, so we can account for this by including cross terms. And we also have what we call other terms. These other terms are some special energy terms here that can be included in order to describe better, for example, hydrogen bonding, pi-pi stacking motions, or other kinds of interactions which are not really covered by either the stretching, bending and torsion or van der Waals and electrostatic energy components. So let's try here to focus here on the first and maybe the simplest of these energy terms here, namely the stretching energy. So what we imagine here is that we have a molecule. Now what we do is that we stretch this chemical bond up here. And as we know here, then we do this stretching here, the energy changes in a way which is pretty good described here by the so-called Morse potential. I have given here the equation here for the Morse potential, and you can see it involves 3 parameters, the dE parameter, the alpha and the R0. Even though the Morse potential here is not that complicated, it can in fact be made even more simpler. If we try here now to look at the stretching energy here of a chemical bond, then in the situation where we are around the equilibrium position of the bond, which is the usual case for a chemical situation here, then a second order Taylor expansion of the Morse potential here, which gives rise to this harmonic function here, actually reproduces the Morse potential quite well. And this harmonic function, which I have tabulated here, is much more simpler than the Morse potential. So what we will do here is that instead of using the Morse potential in order to describe the stretching energy, we will rely on such a simple harmonic function here in order to describe the stretching motion. And you can see we have actually also succeeded in reducing the number of parameters here from 3 to 2. We now only have the parameter Ks and the parameter R0. The parameter R0 here is the equilibrium position of the atoms, while the parameter Ks here, which is referred to as the stretch constant, the bond constant here for the stretching motion, well, this is related to the steepness of this harmonic potential curve here. So if we have a very stiff bond like a carbon triple bond, then we have a very high value for this Ks here, and if we have a more loose bond like for example a Cc single bond, then this value is reduced compared to the triple bond here. So all stretching motions will be described by such an energy expression down here, but we will use different sets of parameters Ks and R0 in order to describe different sets of atom pairs. Of course, if we are not completely satisfied with this harmonic approximation, then we can always go to a higher order in our Taylor expansion and add cubic or quadratic terms, but note, if we do so, we will have to determine further constants K prime here for the cubic term and K double prime here for the quadratic term. So usually we will stay with the harmonic approximation due to efficiency. For the bending motion, we will use an expression which is completely similar here to what we did for the stretching motion, that is a harmonic potential involving a force constant describing here the softness of the bending motion and also the equilibrium position here of the bending angle. Now for the torsional energy, this is a bit different compared to the two other terms, and this is due to the fact that if we look for example at butane here, and if we define the rotation angle here as being around the central Cc bond, then after we have made a rotation of 360 degrees, we should be back exactly at the same place where we started. This is also reflected here in the torsional energy profile. We start here with a value of 0 in the torsional angle, and then moving from 0 and towards 360 degrees, we end up in exactly the same point as we started. So we have a periodicity built into the torsional energy expression, and this periodicity is not found in either the Morse potential or in the harmonic potential, so we need to rely on another set of functions. The functions that we rely on in this case here is a linear combination of cosine functions, which generally is referred to as a Fourier series, and we will get back to this and to work a bit more with this in class. Now, as we know, some molecules, for example benzene, are planar. If we take a look at benzene from a quantum mechanical world, then we know that at each of these carbon atoms here we have a pi orbital standing perpendicular to the plane, and due to the fact that we will have a maximum overlap between these pi orbitals, benzene will become planar. Now, in our molecular mechanical description, we do not have electrons, and therefore we do not have orbitals. So we cannot automatically be sure that benzene will come out as a planar molecule in a molecular mechanical description. Therefore, if we know due to aromaticity that molecules are planar, what we do is that we impose an energy function called an out-of-plane bending or an improper torsional energy function, and this is a harmonic potential again, defined by this equation here. Now you should understand this equation in the way that the phi here is the dihedral angle made up of the C atoms and maybe the hydrogen atom up here. Now if this phi value here moves away from the value phi 0, which in the case of benzene would be 0, then it will cost some energy. So by putting into our force field description these improper torsional energy terms here, we sort of build into the model that it will cost some energy, for example for benzene, to become non-planar. So this is our way in molecular mechanics to impose planarity, for example in conjugated molecules. We also have the van der Waals energy, which involves, as we talked about before, interactions between atoms not directly bonded to each other. The van der Waals energy usually looks something like this. It is very steep here when the atoms get close together, then it passes through a minimum and then it tends towards zero as we increase the distance between the atoms. We usually model the van der Waals energy using a Lennard-Jones potential, which is given up here. In class you will be working with this expression, so I will not go more into detail with this expression here. Now, as we know, atoms do not have a charge. Atoms are neutral. But when we put atoms into molecules, then due to the fact that different atoms can have different electronegativity, we can end up by having residual charges at some of the atomic sites in molecules. This is the case, for example, in water, where oxygen has a high electronegativity, meaning that we have a residual charge of minus 0.8 at oxygen, and then approximately a residual charge of 0.4 situated at hydrogen. This means that due to this charge splitting in our molecule here, we will have electrostatic interactions. Once we know the value of these residual charges here on water and butane and any other molecule, then we can calculate the electrostatic energy due to these charges here using Coulomb's law. This is very simple. This is just the charge A, charge B divided by the distance between the charges. So this is what gives rise to the electrostatic interaction energy in molecules. How we get these charges here, we will talk about in another video lecture. So in addition to these 5 well-defined terms here, we also had the cross terms, which brings corrections to the energy due to the coupling between stretchings, bendings and torsions. We had the special terms, which could be the hydrogen bonding terms, the pi-pi stacking terms, and so on. Note that the non-bonded interactions are not calculated for atom pairs that are connected directly or that are connected via 2 bonds. They are connected for atoms which are connected by 3 bonds, but usually the value for this specific energy interaction is scaled down. We have now seen that it is possible to write up a set of simple functions that makes it possible to calculate the energy for a molecule. We have also seen that in order to perform such calculations, we need to determine in advance a lot of parameters. For example, in order to model the electrostatic interaction, we need to know what is the value of the atomic charges. In order to find out what is the stretching energy in a given molecule, we need to know what is the value of the stretch constant or the force constant between a specific bonded atom pair. So if we think about it, then it means that we really need to determine a lot of parameters if we are to be able to describe all possible molecules in the world. This, of course, is not a feasible situation, and what we do instead is that we rely on the functional groups that you know from basic chemistry, namely that structural units behave similarly in different molecules. So what we do here is that we define a limited set of atom types. For example, we define a type 1 to be a carbon atom which is an sp3 carbon. We define a type 2 to be a carbon atom which is an sp2 carbon atom. We define a type 4 to be a carbon atom which is an sp carbon atom. And we now invoke the principle of transferability, meaning that every time we have a molecule where we meet an sp3 carbon atom sitting in an alkane, then we assign the same set of parameters to this carbon atom. We do the same every time we meet an sp carbon atom sitting in a molecule. So for example, let's look at the carbonyl group. This is a CO group. Then it means that no matter in which molecule the CO group is found, we will always assume that we can use the same value for the force constant in order to describe the stretching motion of the CO bond, and that we can always use the same charges put on the oxygen and the carbon atom of the carbonyl group. So by this, we really reduce the number of parameters that we are to determine to be a realistic number, thereby making it possible to actually do calculations using molecular mechanics. You should be aware of the fact that since we have used here a set of very simplified functions in order to express the energy, since we have used parameters which we assume to be transferable between different molecules, well, then the predictional power of molecular mechanics is limited. The accuracy is usually not that good, and it depends heavily on the parameterization. Usually we use molecular mechanics for calculating energies, and especially relative energies between different conformers of molecules, and we also use it in order to predict which conformer is actually the most stable one. You should also be aware of the fact that molecular mechanics cannot be used for systems having functional groups or atom types that were not included in the parameterization, simply because, well, we don't know which parameters we should put on these atoms here. So indeed there are some limitations, some intrinsic limitations. Further is that since we do not have any electrons in our model, then we don't have any information concerning the electronic structure, meaning that we cannot describe bond breaking, forming, meaning that we cannot describe chemical reactions actually using molecular mechanics, and we cannot describe anything that relates to the electronic structure. So we cannot, for example, use molecular mechanics in order to calculate a UV spectrum of a molecule. Even if we have these limitations here, we still use molecular mechanics a lot due to the fact that it is very fast. It usually takes, well, less than a couple of seconds to do a calculation, and if we don't need high accuracy, then it is still a very useful method. Also, as we will see later on, we can use molecular mechanics in order to describe very large systems, which is not something that we can do using very accurate methods rooted in quantum mechanics.